Hello everyone. Today we will do topological sort. In this sort, um, basically a vertex should appear before all its neighbor or you call as adjacent vertices. For example, this is a graph and 5 has two direct edge towards 2 and 0, right? So now in this output, 5 should appear before both of its neighbors or adjacent vertices. For example, 5 should appear before 2 and 0, which is happening in this case. Here is 2 and 0, and 5 is appearing before that. And same like in this case, 2 has direct edge towards 3. So 2 should appear before 3, and same with 3 and 1. 3 should appear before 1, and same with 4 has two direct edge towards 0 and 1. 4 should appear before 0 and 1 in the output, and there can be more than one topological sorts possible. So any of these should be fine. And yeah, so now let's talk about solution. So if you see, if you think about this problem like carefully, so the whole funda of this is basically a vertex should appear before its neighbor vertices. What if we use a stack and push the neighbor vertices first, and then at last we push the vertex, this vertex? For example, 5 has two neighbors, right? 2 and 0. What if we push 0 and 2 onto the stack, and at last, once all its neighbors are explored or pushed onto the stack, or you can call as visited, right? So at the last, if we push 5, right, that will make sure that um, 5 is printed first before its neighbors, like 520, right? So this is the whole idea. We will be using stack for this. Let's do a quick dry run, like how we will solve this problem. So let's first figure out who is connected to like which vertex is connected to which vertex. So we'll create a adjacency list quickly. So let's take this example. So we'll start from 0. So 0 doesn't have any outgoing edges, right? It have only incoming two edges. So it should point to nothing. Now next 1. 1 also doesn't have any outgoing edges, right? So that list will be empty. Now 2. So 2 have only one outgoing edge, which is 3. From 2 we can reach to 3, right? So this the I'll write 3, and now next 3, right? So again 3 have only one outgoing edge. We can go to 1 from 3, and next is 4. 4 has two outgoing edges, 0 and 1. So we will write comma 0 comma 1. So this is basically the list. Okay. So if there are more than one vertex, you can just write a comma separated list. And when you write the program, you can just use a array list here. And what next? 5 is left, right? So 5 has two outgoing edges, 5 points to 0 and 2. Now it's easier to look like now what we have to do is we have to pick a vertex, and we have to explore all its neighbor vertices, and push that onto stack, mark that vertex as visited, and then move ahead. Let's quickly start. I'll take a stack here. Sorry about this bad drawing. Yes. So we will start from 0. Okay, one by one we will go through all vertex. I started from 0. So now 0 doesn't have any outgoing edges, right? So I can simply mark 0 as visited and push that onto the stack. Next vertex is 1. So 1 also doesn't have any outgoing edges, and 1 we can say that it's fully explored. We can mark this as visited and push that onto the stack. Now let's move to 2. We'll mark 2 as visited, and now if you see, right, 2 have one outgoing edge 3. So we will push onto the stack as we discussed earlier, right? We will push on item onto the stack only if it's all its neighbor or adjacent vertices are already pushed, or and this vertex is fully explored. For example, now 2 points to 3, right? And so uh, then we can't push 3 onto the stack directly. First, we have to explore all neighbors of 3. So we'll just move to 3, and 3 has one outgoing edge to 1, and we will mark 1. So 3 has one outgoing edge, 1, right? So, and 1 is already explored, marked as visited, and it's already onto the stack, so nothing should be done. We'll move back now 3, right? So 3 doesn't have any other unexplored vertex, so we will just push 3 onto the stack, and now we'll move back to 3. Now since 3 is already explored, pushed onto the stack, marked as visited, so we'll move back to 2 and push that onto the stack, because nothing is 2 is explored fully, and yep, so we'll push that onto the stack. So now we'll move to 3, since 3 is already visited, right? So we can just simply move ahead, and now let's move to 4. So 4 have two outgoing edges, or you can call it as 4 as two neighbors, 0 and 1. So let's go to its neighbors one by one. 4 has 0, right? So we move to 0. We go to 0. We see that 0 is already explored and marked as visited. So we will just ignore this, because if it's marked as visited and it's explored already, right? That means it's already processed and onto the stack. So uh, we will visit next neighbor of 4, which is 1 here. Okay, we do the same exercise. We go to 1 and we see that, oh, 1 is already visited and explored, right? So, and it's already onto the stack, so nothing should be done. And next we like, since nothing here for 4 is left, everything is explored, so we'll push the 4 onto the stack. Okay, and next and sorry, we'll mark 4 as visited as well. So next is 5. 5 has two vertices, like 0. We first navigate to neighbor 0, and 0 is already explored and visited. Nothing should be done. We can just ignore it. And now 5 has second neighbor, which is 2. We move to 2 and we see that, oh, 2 is already visited. So we can just move on, and we can push, since all the neighbors of 5 are already processed, so we can just push 5 onto the stack. Now at the end, what we will do is we will just pop this stack and print the items. So if you see match with output, right? 5, 4, 2, 3, 1, and 0. So that's the basically uh, and this is the approach we will be using to solve this problem. Basically, we will push all its neighbors first, and then we will push the vertex onto the stack. Let me quickly show you the code. So code I have also pushed onto my GitHub account here. I'll share the this link in video description so you can go through that. And yeah, so this is the main method, topological sort, and this is its recursive function. Let's see this guy first. Okay, let me open this also. Let me try if I can open. Yep. So so we have to if you see, right, we are keeping track here like which vertex is visited. So this is this visited array, Boolean array, which will take. So that's the like in the line number 57, I just declared a Boolean array visited. And next is to keep track of this uh, to like I'm using I'm using stack here, right? So stack I declared in line number 58, and so this is the for loop, which is basically iterating all the vertices one by one and calling the recursive function if the vertex is all not visited. For example, in this case, right, I was iterating through all the vertices and was doing couple of steps if the vertex is not visited. So that's the thing this for loop does. And once everything is done, we are just printing the stack while stack is not empty. So just do the stack dot pop and print the elements. Okay. Now let's see what this recursive function does. So what it's doing, let's say you passed first vertex, okay, 0, and 0 is passed to this recursive function. What the first thing we are doing, we are marking 0 as visitor, and next thing we are this is array list dot size, and this is array list. What we are doing, we are fetching all its neighbors, and we are if neighbors are already visited, then we are doing nothing and just pushing this vertex onto the stack. For example, if 0 has one or one as a neighbor, if 1 is already visited, so I'll do nothing because it's already explored, right? I'll simply push the 0 onto the stack. So that's what, like, just repeating the same thing again. um, if vertex is let's say second case is if vertex is not visited, let's say if zero's neighbor is not visited, not explored, I'll just call this recursive function and explore that neighbor first, and then push the node onto the stack. For example, let's say it already processed 0 and 1, and we move to 2, and 2 is passed to this function. So this array list dot size we return 1 because this list has one element, right? And it will see that 3 is not visited, okay? And what it will do, it will call the recursive function for 3 and explore it, and once 3 is explored fully, then it move back, and then at last it will push the 2 onto the stack. So that's all. That's the main logic. Now let's quickly talk about the complexity. So here like we are using depth first search of the graph, right? So the complexity will remain uh, as depth first search has, so which is O of E plus V, which is number of edges plus number of vertex. So that will remain same, but extra thing is this space complexity. So if you see, we are storing the elements into the stack, right? And stack will occupy the space equals to the number of vertices. So O of V is the space complexity. That's all. That's pretty much it. So if you have any questions, so just comment on the video. I'll try to answer. If you like my video, please give me thumbs up. And if you want to see more such videos, please subscribe my channel. Thank you so much. Thanks for watching.